Now, the problem is that if you study representation, so what are we supposed to do? To study representations of the little group, right? If it was not for this, then this would be just what I said before, just one-dimensional representation, just the Helicity. Okay? But if you take also this, it becomes a more complicated thing to study. And the point is that the only way to get a representation which is physically acceptable, okay, is to set these M1 and M2 to 0. Okay, this you set to 0 this, and then what survives only is J3. So this is what we are doing. You can set to 0 then, right? This is a representation, right? In particular, when M1 and M2 are 0, J3 is just a one-dimensional object. That is a particular representation. But in principle, you will have also representations of this algebra in which M's are non-zero, are non-trivial. But, okay, I don't have time to enter into this. You can prove that there are infinitely many states in this that you get in this way, and they don't correspond to anything physically sensible. Okay. So, conclusion is that you can forget about this. But before doing that, you have to make some analysis to conclude that this. So in practice, we don't bother about these things. You keep on with this. Okay, this is the story with the massless. So we have just one dimension. So each state is characterized by one quantum number, which is the Helicity. It can be positive or negative, but integer or half integer. That's all. There is no multiplet structure, unlike the massive. Okay, so we have this situation. Now, so we have done this in a particular reference frame, right? Which is this one, or the rest frame for the massive case. Now, the goal, our goal is to these are the two cases, right? Our goal is, and we know, okay, the representation theory of this, in this case is SO3, in this case is SO2 or U1, okay? Representation theory is well known. Well, just what I said, right? This 2s plus 1, 2s plus 1 thing. Here will be just a phase, a single phase, right? But our goal is to study representations not of this little group, but of the full group, which is the Poincaré group. Of which these are just very small subgroups, right? The key point is that from representation of this, you can construct a representation of the full Poincaré group. This is the whole point, the key point of this construction. First of all, so we have P mu's and the translations and the Lorentz, right? These are the generators of the Poincaré algebra. And so we choose a basis of eigenstates of P. Okay, P mu on this. This is an extra quantum number that refers to the spin. Or the Helicity, depends whether you are here or here. And then this is P mu Ps. Okay, so these are eigenstates of the four momentum. Okay, so we choose a basis on this given by this object, eigenstates of P, and so our goal is to do what? To study. So given any four momentum, right? Study represent something like that, G of lambda on Ps. where P is an arbitrary form momentum which obeys, of course, P square equal to M square or P square equal to 0. But apart from that, is arbitrary. Okay. So this is our goal, to see how these operators act on this base. Okay. And so this is, so then you see, point is that what we see that representations of the little group can be lifted to representation of the full group in a way that I'm going to sketch. Okay, so first of all, we have a reference momentum Q given by this or that, and we can choose a Lorentz transformation that acting on Q gives our arbitrary form momentum P. Okay. Now this L of P is to some extent is not completely fixed, right? Because given a Q, I can apply to Q any element of the little group. This thing would not change because the little group leaves this invariant, right? So this is not completely fixed, right? You can multiply this from the right by an element of the little group, which I denote by W. Okay. But there is some standard choice for L of P, for example. In the massive case, you can get any momentum P with this property by doing the boost that you studied. You remember this, the boost that you studied by acting with S on the gamma matrices. That allows you to transform the rest frame momentum to any momentum, right? In any direction, no? To E N, right? P. By choosing the parameters, you can, and this is an arbitrary with, of course, E square minus P square equal to M square, right? So you can choose for that this Lorentz transformation. And for the massless case, well, the massless case, of course, you have E, the starting point is this, E 0, 0. Then you can do a boost along the Z direction, okay, which multiplies this by something like that. This is the rapidity. For this particular form momentum, this is just a dilatation by this e to the omega. Because the cos, the general formula involves cos omega, sinh omega, cos omega. But if P0 and P3 are the same, then you immediately verify that the cosine plus the sine is the exponential, right? And so this is why you get e to the plus omega. I don't know if suppose you have EE, say in 2 dimensions, okay? This is P0, this is P1. Do a boost on that, okay? This is cos omega, sinh omega, cos omega, right? This is this, no? But since this is equal to that, this is equal E cos plus sinh, right? And similarly, this is cos plus sinh, right? No? You agree? But then e to the plus omega plus e to the minus omega plus e to the plus omega minus e to the plus omega, right? The e to the minus omega cancels, and what remains is this, in both. if you do a boost along the third direction, of course, right? And then you can do a rotations. You can rotate this into any direction you wish. This would give the more general light-like vector. Okay, so there is a choice for this L. You can make standard choices for this. Okay. Okay. So then we define the states. So we start from the state. We start from the state Q S, where Q is what the rest frame or this thing. We apply LP, and then there is some normalization. This will be defined to be PS. Okay. The definition. So this transforms this form momentum into this form momentum. And this is normalization. On the other hand, if you apply, say, some G of lambda on PS, which is what we want to study, right? What can you say about this? Well, this will be, this is like a state of capital P, right? P mu on PS is P mu PS. No? Okay. So if you apply a Lorentz transformation to this will give a momentum lambda P, right? So this will give lambda P. But in general, this S can be mixed, right? We can have something like CS S prime, PS prime, right? But sum over S prime, of course. This is what we can have, right? All we know that this is eigenstates, so this is eigenstates of right? This is what we know. So this is what should happen. But so the goal is to study this. What is this thing here? Because this clearly gives should give a representation of the G, right? How it acts on the states, how it mixes the states, tells you what representation you get, right? So then let's study this. So you have G lambda on PS. This is what? This is PS, on the other hand, is this, right? There is this normalization, and then G of lambda LP on QS, right? Okay. Which I can write also in this way, G of lambda LP, right? Because of the group properties, right? This is a group element, no? This and that. Okay, but now let's do some trivial move and rewrite this in the following way. This is G of L lambda P, G minus 1 of L lambda P. This is 1, right? G minus 1 of the same group element, right? I've done nothing. And then I write G lambda L of P on QS, right? So I've just inserted the identity here. So what is L of lambda P? Is the particular boost which takes Q to lambda P instead of P. Okay. So L of lambda P takes Q to lambda P. Is the analog of this. Now let's look at this thing here, this element here, I can write this also in the following way. Let me rewrite it a little bit. This is n g of lambda, sorry, L of lambda p, which is this thing here. I keep it like that. And this is g of L minus 1 lambda p, right? Because of the group properties again, right? G minus 1 is G of the inverse, right? And then lambda and then LP on QS, right? This is what it is. I've rewritten this here. Now, the crucial observation is the following. What is this thing here? What is this Lorentz transformation here? What it does? Well, definition. You start with this applied on, so you start from Q, you apply L of P, you go to P, right? Then you apply lambda, so this is L of P. Then you apply lambda, this goes to lambda P. Then the inverse takes you where? What is the next step? What is the next step? Is the inverse of what you did, right? Remember that from Q, L lambda P gives lambda P. This is the inverse operation of that, right? So it takes this to what? Huh? I heard some. To Q. To Q. So you start from Q, you go back to Q, right? I repeat it again. Q. Apply this, you get P. Apply lambda, you get lambda times P. But then L minus 1 of lambda P is what takes you from lambda P to Q, back to lambda to Q, no? The inverse transformation. Right? So what is this transformation? Not necessarily. Not necessarily. You transform Q into Q. So what is more generally than, could be the identity, but more generally could be what? Phase. Remember what is a little group? Little group is transformation which leaves invariant some vector, the vector Q, right? The little group we call it W, is what? Leaves Q invariant. No? This is definition. This is a subgroup of the Lorentz transformation. The definition of this. So this is an element of the little group, which depends on lambda and P and so on. So you see, after all this manipulation, we went back to the little group, of which we know that the representation, right? Because this little group is what? Is either SO2 or SO3, right? Whose parameters depend on this in maybe complicated way, but in any case is an element of the little group, leaving Q invariant, right? So then we have something like, let me continue with that, N, G, L, lambda P. And then this, acting on QS, this is a representation of the little group, right? So this will be D, say, S prime on Q S prime, sum over S prime. You understood the sum over S prime, right? Right? Because this is what we started from, right? we said, okay, the representation in the reference frame that we choose, say the rest frame for the massive or the other frame for the light, transforms under this or that. So this SS prime is a matrix of SO3 or a phase in SO2, which depends on these parameters here, which enter here, and depends on which representation you choose. Right? So we end up with the little group again. After this, you know, this is the starting point, right? This is general order transformation. And then we have to close here. What is this? Then we continue with that. So we get that this is n. So G of lambda of PS is n dSS prime. And then we have G of L lambda P acting on QS prime, right? I've taken out, these are numbers now, these are matrix elements acting on this, depending on lambda and P, okay, whatever, but. And now what is this here? Well, this is, remember something which I raised, what did this say? We said that G of L P on, so no, let me write it like that. P S is N G of L P on QS, right? This is what we said, no? But now instead of P, we have lambda P. Okay, so this I can write like that, lambda P. This is lambda P. This will be N of lambda P. Okay. So then this is what? Is lambda P S prime divided by this normalization, 1 over N lambda P. This is N. You have to follow the steps. Okay. So the conclusion is that what we were after was to see how this act on an arbitrary momentum state, right? The answer is that there is some normalization, some numerical factors, which actually you can set to 1 in some choice. And then we have d SS prime, okay, lambda P S prime. That's all. But suppose there is a normalization, a way to normalize things such a way that this is 1, just not to confuse with many ingredients, then you got what you wanted, right? Because the action of an arbitrary Lorentz group element on an arbitrary form momentum, okay, in the class, of course, on shell, P square is equal to 1 square, P square equal to 0, that is goes there, is up to this numerical factor, just the action of the group that we know very well, either SO2, in which case this is just a phase, or SO3, in which case these are the 2s plus 1 times 2s plus 1 matrices which represent SO3 on these states. But what is the important point, you see? Important point is that these are unitary matrices, because the representations of SO2 or SO3 are unitary. Okay? So we got unitary. You can check that this furnished representation, because these are representations, and check that they are unitary representation of the Lorentz, the full Lorentz group, okay? But they are infinite dimensional. Why? Because they are not just these matrices here, you see, which are 2s plus 1 times 2s plus 1 in the massive case, or or phases, because they depend, the states depend on the momentum. The momentum is a continuum variable, right? So you have a set of infinitely many vectors, right? Labeled by P, all in addition to S. If it was only for S, it would be finite dimensional. But the fact that you have the momentum means that this is an infinite dimension. Okay? Otherwise, you couldn't get a unitary representation. Let me just elaborate a little bit on this. You can prove that you have to choose. You have to choose, of course, we have a basis PS, right? You have to normalize them, right? You have to choose an inner product between the basis elements, right? We have to say what is PS, P prime, S prime, right? We have to fix this. Since P is continuous, it will be a delta function, right? This would be delta P minus P prime, okay? And but there can be normalization here. That, of course, delta SS prime, they will be there because they will be orthogonal for different spin components. But there are various normalization. There is one which is for which you can prove that for this normalization, in fact, these n are equal to 1, which is this one, 2e. I'm discussing the massive. Now, why this is? Because this is an invariant. This is the Lorentz invariant. Normalization. Right, because remember that if you have an integral d for p delta p square minus m square, right? This is Lorentz invariant because this is d for p, this is Lorentz invariant, right? And then if you rewrite it as dp, this puts on shell, right? This is p square minus m square is p0 minus square root of p square plus m square, right? Times p0 plus square root of p square plus m square, right? And if you choose, you put here a theta, you choose the positive energy. Okay, then you can do the integral over P0, right? And this becomes over 2e, right? Square root of p square plus m square, because you pick this, but then there is this coefficient which goes down, right? Delta of this, no? You have delta of P0 minus that times P0 plus this. So delta takes P0 equal to the square root. You substitute it here, you have 2 times the square root, which goes down, right? Delta AX dx is 1 over a, right? So this is the Lorentz invariant measure, and this is why there is 2 here. So when you integrate with the Lorentz invariant measure, this cancels that. Okay, this is one normalization. So we can prove that with this normalization, this n is equal actually to 1. And then you can prove that this G is unitary. What you have to prove? You have to prove that, say, P prime S prime, G dagger lambda, G lambda on PS, right, is equal to P prime S prime PS, right? So this is equal to 1. This is unitary. G dagger G is 1. You can prove that. So I don't want to enter into many details. The idea was to give you a flavor of what is going on with this representation of the Poincaré group. Of course, we have this, right? This is Lorentz part. The translation part is trivial because we have chosen these states to be eigenstates of the form momentum. So they are clearly representations also of the full, right? So you have that e to the I a p on ps is just e to the I a p ps, right? This is obvious, right? This is the operator, and this is the number. So we got this representation, which is unitary, infinite dimensional, and these are the single particle states, right? Because this is what we started from, right? These are the physical states that you will use when you compute scattering amplitudes. Physical states are states of this form, right? Which depend on the momentum, the spin, and they are representation of the Poincaré group. Okay? So this is the approach that you can find among other books on the Weinberg's book. The starting point, Weinberg's book on quantum field theory, starts with this, with representations of the Poincaré group, and so this is the key, again, a key point is that you can lift the little group, which is something well known. It is a compact, like SO2 or SO3. You can lift it to the full Poincaré. Okay. Any questions?
I had a question from yesterday's, from the last day's lecture.
Yeah.
So last day we saw that if we construct the generators like J plus and J minus, they build like separate SU2 algebras. And then we said that we can represent SO13 as direct sum of two SO2 groups. So yeah. So
Okay.
yeah. So but SO2 groups are unitary, but
Yeah, no,
SO13.
I mean, yeah, okay, this is what I'm saying. It's not very precise. It is, you're right, of course. SO13 is lower, it's non-compact group, right? SO2 are compact groups, right? So the correct statement is SO4 algebra is the sum of two SO2 algebra. That is for sure true, okay? But for the Lorentz, cannot be true, right? Although you can, I mean, in practice is as if, right? But the more precise statement is that you have that SO1, 3, the Lorentz, something like that, is not the sum of two SO2 algebras, for the reason that you said, but is actually the sum of two conjugate SL2C algebras. You see, it cannot be two independent SL2C because SL2C has six generators, right? So if you had 6 plus 6, it's too much, right? But in a sense, you could write SL2C plus the conjugate SL2C, something like that. So this is more precise statement, which in many respects, when you study representation of this in terms of these, is as if these were SO2, because the way they represented is not very different, right? Like for SO2, when you have SO4 is SO2 plus SO2, right? This is correct. Then the representation here are labeled by two numbers, right? J1 and J2, right? No? Corresponding to this and that, right? So the same is true here. But because also here you can represent this in the same way, J1 and J2, two integer or half integers, okay, like here. But they are not, these are the spinor representation of SO2, which are unitary representations. Whereas here, they are not unitary representation, they are, so start from, say, the 1/2, you can start from 1/2, say 1/2, 1/2, 1/2, 0, 0, 1/2. This is similar to that. It's very, I mean, it's the same. But the difference is that these representation here are not unitary. This is the, say, chiral spinor, one chirality, this is the other chiral spinor, and so on. But the way you write, you label them is the same. But it's not true that SO13 is the sum of two SO2s.
But at the Lie algebra level, it's true, right?
No, again, because the point is in the algebra level also, if you note, there was some homework that they have to do. The difference between these cases is that in this case, the two algebras are written like that, Ji plus or minus I Ki over 2. There is I here. Whereas here is Ji plus or minus Ki over 2. This is the difference. This is here, and this is here. So you notice that what is the difference? There is no I here, right? So these are really independent. The plus and the minus are two independent objects. Here, the plus and the minus are not independent because one is the conjugate of the other, right? It's like having, this is the example I made, right? If you have ZZ bar or X plus, X minus, these are complex conjugate coordinates. No? This is X plus IY, X minus IY, right? Here is X, say, in the light cone, if you are in Minkowski, this T plus X, T minus X. Okay, this is Minkowski, this is Euclidean. So here you have ZZ bar, which are complex conjugate of each other. Here you have T plus X, T minus X, which are completely independent, right?
Also, maybe we can say that because we are considering a group like SO13R, so in general, we are allowed to take combinations as a real number times the generators and take the linear combination, but not like complex number.
Well, we are complexifying in some sense, right? The
Yes.
fact that you are complexifying. Also, SL2C, right? SL2C
yeah.
is complex, no? Right? Well, yeah. But you can think of it as real. No? If you, in SL2C, you have sigma i's and I sigma i's. Where you consider formally this and that completely different objects. And you take a real combination of these. So in this sense, you reinterpret the complex SL2C as a real. Yeah. Well, the same, even more trivial situation. If you go from SO2 to U1, right? Even there you have a complexifier, right? U1 is into I alpha, where SO2 is a 2 by 2 matrices with real entries. So then I repeat it again, this is the correct thing for S13. Although there is this formally, at the formal level, the way you represent the representations are are the same, but the meaning is very different. One case is unitary representation, the other is not.
I have
sometimes a bit confusing, I agree, this type of thing. Yeah. See, yeah?
I have another question. So here we have constructed the representation of Poincare group by using little groups. But is there any approach to construct the representation using like the way we did in case of SO13? We found out the set of commutating operators, and then we labeled the states as the quantum numbers corresponding to the commutating operators. So is there any approach?
Well, this would give, this would give this picture, right? Finite dimensional representations, right? But let's say one thing here, okay, let me take back what I said. You could do that and study, even in the case of SO13, infinite dimensional representations. Okay? What we discussed were the finite dimensional representations, right? You mean like you study representation when you have, you are in the other course, you pick a Cartan subalgebra, right? And you construct a representation, raising and lowering, things like that, right? You could do the same also here, also for the Lorentz group. But if you want to study, okay, so this would give the standard finite dimensional representation, which are labeled in this way. Okay.
I mean, if I add the other three generators, I mean the momentum operators in it. So
okay, no, then this is what I wanted to say next. I mean, what we are doing here is really studying Poincare, not Lorentz. You see, because we are using as a basis states which depend on the momenta, right? So it's crucial that we have the full Poincare algebra, not just the Lorentz part. Because we are representing everything in terms of momentum eigenstates, no? Now, there is a similar picture, which gives also representation of Poincare when you remember when we said, we discussed the transformation of the, we said psi prime, x prime is S of lambda psi of x, right? No, this was the form that the spinor transformed under Lorentz, right? And the same A prime mu, x prime is lambda mu mu. Okay. So these are also, now you can write this in a nicer way. Psi prime of x, you can write as S of lambda psi of lambda minus 1 of x. No, because x prime is lambda x, right here. Write it in this way. Okay. You see, also this is a representation of the full Poincare. This is the field. These are called fields, right? This is a field, which depends on space-time coordinates. This is also a representation of the Poincare, because this is the way the Lorentz transformations act, but Poincare is just giving the translations, right, on X. No? So it's not very different, right? So you have both of them. However, if you do that in this way, in fact, I have a chapter in the lecture notes which discusses this. When you represent the Poincare group on fields, which depends on space-time. Okay, but these are non-unitary representation. They are infinite dimensional. Why? Because they depend on X. X is a continuum variable, right, over the full Minkowski space-time. So they are labeled by infinitely many indices, right, on top of the spinor indices, right? There is X also. Like here we had P. But the difference is that this is not unitary, because these are not unitary. These are the standard finite dimensional representation of the Lorentz group, and they are not unitary. Okay. I have no time to discuss this. If you want to go through this chapter, which is not difficult, which is 14. But yeah, fields somehow, you see, the fields, as you will see in quantum field theory, contain more redundant things, that they are not containing just the physical degrees of freedom. The single particle degrees of freedom are containing what I discussed before, which contains the physical degrees of freedom. For example, the photon has two helicities, +1, -1. If you discuss this thing here, these contain much more electromagnetic potential. There is gauge invariance, and so you have to do some work to extract from here, from Maxwell's equation, to extract the physical degrees of freedom. Okay. Whereas the discussion that we had before about the Poincare group representation is just designed to describe the physical degrees of freedom of the particles associated with particles. And as such, they are unitary. You will see this better in quantum field theory course in QED. Okay, so we have to discuss some homework also. I will do it. You have any question, other question concerning the previous things? Anything?
Yes, Prof. I have a question, please. Yeah. It's about what we discussed the last class. We talked about left-handedness and right-handedness of particles.
Yes.
So, could you please shed more light on the conditions that must be satisfied before we can say a particle is either left-handed or right-handed?
Okay, left-handed, right-handed is we discussed the first of all, we are in the massless case, right? And so in the massless case, if you choose a convenient basis like which we have chosen, the sigmas, right? 0, sigma mu, sigma bar mu 0 for the gamma matrix, although it's not necessary, you can do any basis, but some bases are more convenient. So on the Dirac equation, gamma mu d mu on psi, m is 0, and then you see if psi is phi and chi, right? You have two decoupled equations, no? Sigma mu d mu on chi equal to 0 and sigma bar mu d mu on phi equal to 0, right? Okay? And now these equations actually, so sigma 0 is E is the identity, okay? So this is just E minus sigma dot P, right? On chi equal to 0, this is E plus sigma dot P phi equal to 0. These are the two equations, right? Okay? And so what we said, okay, these are very simple equations, divide by E, and you find that, for instance, chi is satisfies this equation, sigma dot P over E equal to chi. So this is plus, and here is minus, right? These are the two equations, right? Plus here and minus here. But then we said, okay, what is this operator here? This is the Helicity, right? Because this is sigma dot P over modulus of P, right? E is modulus of P. So it's sigma dot n, right? So this eigenstate of this operator with eigenvalue +1, and this is eigenstate of the same operator with eigenvalue -1. And this is the these are the essentially up to a half factor, the two helicities. This is Helicity plus, and this is Helicity minus. Okay, so what is the Helicity? Well, semi-classically is the spin, the projection of the spin on the direction of flight of the particle, right? So if the particle flies like that, it means that in the plus case, it is oriented parallel to the direction of flight. This would give this plus here, or it is oriented opposite. This would give minus. No? Now, the terminology is that you say this is right-handed, the plus, and this is left-handed. It means that if you have a picture of the angular momentum as something which rotates, this goes like that, clockwise, and this goes counterclockwise, if you wish. So this is the meaning of right-handed and left-handed. This refers to neutrinos. And
Sorry.
yeah.
May I ask another question, please? Yeah. In the non-relativistic limit of the Dirac equation, there was a particular answer we used then, and that was that the high h, the chi dt, is far less than m naught c squared chi, right? So what I want to know is this.
Completely, we had at some point we could solve. We had phi and chi, right? Yes. And we could solve, instead, okay, you can solve if chi is sigma dot p minus EA, right? Over 2m. Yeah, we had this, right?
Yes. And actually, I think the answer was made particularly before we even reached this level.
Sorry?
I mean, the answer I'm referring to was made before we got the value of chi. Like from the two component formalism, when we have the matrices, that IH d dt of chi and phi. There was a particular.
Well, what you were saying. Can you speak
I'm saying,
lower?
okay, when we're trying to solve the Dirac equation in the non-relativistic limit, there was a particular assumption that was made.
Yes.
And the assumption is that the modulus of IH d chi dt is far less than the modulus of m naught c squared chi.
This one.
Yeah, absolutely. So now my question is this: why is the assumption made on chi and not on phi?
No, because on phi we didn't have such a thing, right? You remember the equation for chi was I dt chi, then there was plus sigma dot p minus EA to m, right? And here we had plus phi, right? And plus 2m chi, no? This was the structure, right? Right?
Yeah.
Whereas for phi, we had, for phi, the point is that phi sigma, this is chi, right, over 2m. That's it. The point is that in one of the two equations, the mass was cancelling. You remember we started from chi and phi and chi, and we took out e to the minus imt. We took out this factor here. Now we are assuming that the mass is big. No, because no relativistic limit, the mass is big compared to velocities and things like that, right? So once we did that, here, here the mass was cancelling, whereas here the mass was adding, right? So then there is no way here, I mean, we don't have a mass term, right? Here we have a mass term. And we say, okay, this is much bigger than that, so we neglect this.
Okay.
But here we don't have a mass term, right? What can you say? dt phi small compared to what? I mean,
I see it now.
and this, let me, since we are raised this point, let me just mention how the calculation should have done, which I didn't do it, but I saw some did it correctly, some other. At some point, one has to compute essentially, right? There was I dt phi is sigma dot p minus EA over 2m squared, right? This was the Schrödinger-like equation. Now the whole point was to compute this thing here. Sigma, let me call this pi, sigma dot pi squared. No? Now the way to do it is to use the algebra of the polymer. Sigma I, you have sigma I pi I, sigma j pi j, right? So this is sigma I, sigma j, pi I, pi j. You have to compute this, right? Now sigma I, sigma j, use this. Delta j plus I epsilon I j k sigma k. There are two terms. There is a delta for the symmetric part and antisymmetric part. And both contribute, because if you use this thing, you will have sigma I So it's delta ij pi I pi j, right? Plus I epsilon I j k sigma k, right? And then you have pi I pi j. But now this is antisymmetric in ij. Okay, so I can just take the commutator here of these two and divide by 2. Okay. Now this gives pi square that we have to compute. And this gives an extra term. See, this is a commutator pi I pi. Now it's a curious thing in presence of magnetic field, you know. What is pi I, this thing here? Pi I, which is pi minus EAI. This is essentially the velocity operator, right? This is n vi, right? No? Remember when you did this classical analysis of a point particle with, no? Now, so this is the velocity operator. Whereas pi pj commute, right? This is the momentum, a base canonical commutation relation. But the velocities, which are these, do they commute? No, they don't commute, because if you take pi I pi j, this is what? Is pi minus EAI, pj minus EAJ, right? You have to take this commutator. Now, this with this is 0, this with that is 0, but the cross term is not 0, right? Because this is minus EAI pj, right? Minus PIAJ, right? Right? Okay. Now the point is that P is a momentum, right? Is a momentum is represented by a derivative with respect to x. So Pi is minus I di, right? So you see that these don't commute, no? Because if A depends on x, no? If A depends on x, they don't commute. And indeed, what it gives, this gives up to a factor I, E, Fij, right? The field strength, if you compute it using this, this gives Fij. The commutator, this gives, what is Fij? Fij is di Aj minus dj Ai, right? This gives this. So in presence of some magnetic field, the velocities don't commute. Okay. And so then here you have to use this, right? Plug it here. This, what it gives, pi I squared, this gives, so if you have done the calculation, this gives the orbital momentum part, the coupling of the orbital momentum with the magnetic field. This gives the coupling of the intrinsic angular momentum with the magnetic field. Right? So let's see, this term here is di minus this is to compute, right? So this is pi squared. This gives the standard kinetic term, clearly. Minus E squared, AI squared, plus, no, this with that. This gives something. And then you have plus, minus actually, pi E AI minus E AI, PI, right? So this, you have the term minus E, PI, AI acting on here, right? And then you have also, when this goes here, it adds to that, minus 2E, AI, PI. Right? Now you have to be careful because P does not commute with A. So there is a term which P acts on A, which is this, and then a term where you can move it here, right? And then it becomes the same as this. So it's a factor of 2. PI AI actually depends, but in our case is 0, because what is AI? We said AI is something like epsilon I j k x j h k maybe. But when you differentiate, you take di pi ai of this acts on x, but gives a delta ij, and this is 0. So this does not contribute, but this contributes, and this gives. Now, if AI is epsilon I j k x j h k, and then this is pi, you take out hk, but this is the angular momentum, right? This is L, Lk. So this is the orbital part, and this is H dot L, right? This comes from the first term here. And this gives instead the coupling H S, because you have the Pauli matrices here. And the whole point is to check that between the two there is a factor like that. Now, if you did the calculation correctly, you would have found this, where S is sigma by 2, right? This was the calculation.
Sorry, on that note.
Yeah.
Yeah, on that note, like, is it possible to solve the Dirac equation in the non-relativistic limit without coupling it with electromagnetic field?
Sorry. Is it possible to?
Is it possible to solve the Dirac equation in the non-relativistic limit without coupling it with electromagnetic field, without minimal coupling? Is it possible?
Yeah. You will have just the Schrödinger equation, right? If this is not there, you get this. That's all, right? The free Schrödinger equation. Put equal to 0, A equal to 0. No? So this gives non-relativistic limit also in the case where you don't have external electromagnetic field. Just the free case, no interaction. But this is more interesting, right? What else? Yeah, another thing I wanted just to comment is, let's see if there is anything else. Yeah, we had some discussion the other time about the condition. So we discussed the condition of spinors to be Majorana, right? To be real, which means that the charge conjugate of the spinor is equal to the spinor itself, right? This was the Majorana condition. No? Psi C is equal to B, say, psi star is equal to psi is a kind of reality condition. And indeed, if you choose a basis of gamma matrix, which is a Majorana basis, in which all the gammas are imaginary, which you can do, which is, I indicated how you can do that in some of the homework. Okay, then this is just psi equal to psi star. Okay, now it's clear that this, you can do the same thing for a scalar field, for a Klein-Gordon field, right? Phi star is equal to phi. No. Which means that the field is real, so the solution again, box plus m squared phi 0, right? But you see, when I said, so the reality condition would mean that there is particle antiparticle, which you have to learn what it means. Okay, you will learn it in the next course. But anyhow, what I said is that they are related to positive and negative energy solutions, right? We said for the Dirac equation, those which goes like e to the minus I k dot x times u, and then the other was v e to the I k dot x, right? This was positive energy, negative, and u and v were we wrote them down, right? We solved that completely. Now, it's clear that if you are, and for the case of the phi of the scalar field, is even simpler, right? Because scalar field, the positive and negative energy are phi is e to the I minus I k dot x, and phi e to the I k dot x. This is positive and this is negative, right? That's all. You don't have the u's, right? Which comes from the Dirac equation. But now you see, if you have a field phi, which is real, no, like that, then these are not allowed, right? You cannot speak of positive energy, negative energy, right? Because this is not real, it's complex. This is also complex, right? So you need to construct a real solution, right? How do you construct a real solution? Well, for example, you take this plus the complex conjugate, right? So, I don't know, phi, so this is some number here, this is another number. But if phi has to be real, you have to sum phi plus phi star, which is a e to the I k dot x plus a star, complex conjugate, e to the minus a k dot x, right? You cannot separate the two, right? Because phi is real, right? And so it's clear that the notion of particle antiparticle does not mean much, right? Or unless they are the same. This would be, suppose A is equal to 1, this would be something like the cosine k dot x, something like that, right? This is real, but this is not real by itself. No? And the same is true for the spinor, for the Dirac equation. You will have to combine this and that and construct some real solution. Yeah, to show you that there exists such a, I mentioned the Majorana representation. and I said that there is a unitary transformation, right? U was 1 over square root of 2, 1 sigma 2 minus sigma 2, 1. If you conjugate the Dirac basis, I think the Dirac basis, I hope it is like that. With this, U gamma 0 U dagger. This is this thing here. U dagger, I'm not sure this is true. Yeah, okay. So U dagger is what? U dagger is 1 over square root 2, 1 sigma 2 minus sigma 2, 1, right? Is this unitary? U dagger, U must be 1. This times that, 1 sigma 2, 1 sigma 2 gives a factor of 2, 1/2, so this is 1. This with that gives 0, 0, 0, right? So this is a unitary matrix, this one. And it should be that if you conjugate, say in the Dirac basis, we had that gamma 0 is 1 minus 1, right? Let's do U dagger gamma 0 U. So this is 1/2. U dagger is this 1 minus sigma 2, 1. 1 minus 1. And this is 1 sigma 2 minus sigma 2, 1, right? This is what you have to do. Let's do this with that. This is 1 sigma 2. And this is sigma 2 minus 1, right? This with this. And then you have 1 minus sigma 2, sigma 2, 1, right? And so this is becoming what? 1. No, it's not, doesn't work. There must be some mistake. No, sigma 2 minus 1, right? And so this is what? Yeah, this is 0. This is minus sigma 2. This is sigma 2. This is 0. Yeah, okay. Yeah. So sigma 2 is imaginary, right? So gamma 0 becomes, here it was real, no? This is a Dirac basis. If you do this conjugation, you get gamma 0 to be gamma 0, say, Majorana. It's purely imaginary. And it should be true also for the other 3 gamma matrices. You get a purely imaginary gamma matrix, in which case the reality condition becomes just psi equal to psi star, the Majorana condition. Another homework that I indicated, I don't know, which is there. I don't know if some of you did it, was to check what are the symmetries of the Dirac Hamiltonian. Dirac Hamiltonian is alpha, right? Alpha dot P plus beta M, right? With what generates, with what operators it commutes. Okay. Well, if you had just the free Schrödinger operator minus box 2n, right? Clearly, this is a SO3 invariance, right? Because this is the Laplacian, right? And even if you add some central potential like that, this is SO3 invariant, right? Now, what is the invariant? So you can try various things. There are, the angular momentum is the orbital one, right? Which is I epsilon I j k j pk, right? So L1 is at 2p3 minus 3 p2 and so on. This is the angular orbital momentum. Then you have the intrinsic one, which is SI, which is sigma I over 2. Okay. And then there is also the helicity operator, sigma, which is n dot j. That's what. And dot, I think it's just dot alpha, right? No, alpha is off diagonal. And dot sigma 0, 0 sigma. Is this, right? Helicity. Spin along the direction. So there are these three. So with what the Hamiltonian commutes? Well, you see, does it commute with L? Is it rotational invariant under the orbital part? Well, clearly not, right? Because here is P, here is X, right? They don't commute, right? What about the intrinsic part? Again, oh, so this is sigma I, right? You have to use the 4x4 matrix. This again does not commute with, well, with this part. No? But what commutes with that is the total angular momentum. J is L plus S. So the two contributions cancel each other, right? Which is what should be expected, should be the total angular momentum symmetry of the problem, right? And also, one can check that the chiralic, the helicity, this operator commutes with them. So the helicity is preserved by time evolution because this commutes with, so J commutes with H and sigma commute with H. So these are the symmetries of the Dirac-Hamiltonian. This is Other questions? If you want, we can meet one more time before the exam. What do you think?
Prof,
Yep.
you just made mention of meeting one more time before the exam. Sorry, could you, when is the meeting going to come up? I mean, when are we meeting? When next?
When, I don't know, for me, any day next week. Other agree? When? In the middle of the week? Wednesday. Okay, for me, yeah, would be okay. Wednesday, okay, Wednesday. You can meet Wednesday, same time, usual time, 2 p.m. And
No problem then.
huh?
I said no problem about that. No problem about that. It's okay.
Sorry?
I said it's okay. It's okay. Since you said Wednesday, Wednesday is okay.
Wednesday, 2 p.m. Yeah. There were also some other, some of you tried, did actually, not tried. There is a nice observation that, you know, it is this at the end of, at the end of chapter 3, it is shown, chapter 8, sorry, how you can diagonalize the free Dirac Hamiltonian. Try to do it. You're the one that HD is alpha dot p plus beta n, right? You can do a unitary transformation. U is e to the minus gamma. The gammas are the usual gammas. Dot p times theta. This is the unit vector. This is unitary, right? Because the gammas are, is it? Yeah. The gammas are anti-admission, no? U dagger is e to the plus gamma, right? Dot p theta, no? Theta is some angle, some angle, right? So this is u to the minus 1. Now you can choose theta in such a way that the new h, which is h prime d, is e to the u to the minus 1 h d u. U minus 1 is the same as u dagger, but okay. So this is a unitary transformation. So if hd is Hermitian, also h prime d is Hermitian. So you have to take this and do this operation here, right? to do that, it's convenient to write this, expand this, right, in cos, and will be cos, not cosh, because this is unitary, right? And yeah, the usual thing, and then conjugate h, which is this. So you have to commute the alphas with the gamma, no? And then there is a theta such that this thing is very simple. It's diagonal. It's a 4x4 matrix, which is the matrix beta here. Beta was gamma 0, right? Beta is 1 minus 1. So it's diagonal. Times the energy, p squared plus m squared. This is called as a name, folding von Thuisen transformation. It was discovered many years ago. You see, this transformation, it brings you h into this form, right? This is E minus E minus E. It's diagonal. It has two positive and two negative energies, right? That is unavoidable, right? E minus E minus E. So there is a theta, you can check, verify that, such that this unitary transformation on the Hamiltonian, the free Hamiltonian, gives just diagonalizes the Hamiltonian. Okay. So this is something that, again, is an exercise in algebra of gamma matrices. Yeah, this is Foldy von Thuisen. Right. I don't know if we have other exercises. Another thing that I can, yeah. We said, right, that there is a map from SL to C to SO13, right? Actually, one can prove that this map covers, is not clear, right? That we can get any element here from this action, G dagger, and then suppose you put here G sigma dot P, sigma mu, P mu. This is the form momentum, right? This is P prime mu, sigma mu, right? And this is an SO3 transformation, no? And yeah, what is not obvious, it's obvious that this is an SO3 transformation, but it's not obvious that all SO1,3 transformations living here can be obtained this way, right? It's not obvious, but it is true. You can prove that. It requires a little bit of work, okay? In other words, that this map is home to. All elements here come from some transformation. Now, suppose you take for P, you take the two cases that we have been discussing. One is M0, the rest frame of a massive particle, and the other is E00E. then the little group, no, you can ask the question, what are the transformations G which leave either this or this invariant? You should recover the little group from this point of view, right? From the point of view of the set to C. Why don't you do that? This is very simple. This is a little bit more involved, but this is very simple, right? P mu, P0 is M. And so there is only sigma 0 here, right? So how you recover SO3 then? Remember, this is G dagger, right? G. And these are elements of SL2C in general, right? So this is very simple. This is a way to get a little group from this point of view. Instead of working directly here, you work here. All right. So next week, okay, Wednesday, I will send a message. Maybe try to go through the material and try to clarify some issues that maybe you are not that clear, and they are still not clear, we should discuss it. Okay, bye.